All right, so what I want to do today is I want to talk about recurrence relations. So, recurrence relations. Everybody has seen at least something on recurrence relations because we've done the Fibonacci numbers. So this is one of the prototypical examples. The idea is later terms in the sequence are defined in terms of the previous terms. So for example, I could have an is equal to f1 of n, an minus 1, plus dot dot dot, plus fg of n, a n minus g of n. If I write something like this down, this would be an absolute nightmare to solve in general. The depth, the number of terms I have, is allowed to vary. The coefficients is allowed to vary. The only thing that's at least somewhat good is it only depends linearly on the previous terms. More generally, you could have, an is some function that depends on n of coefficients a1, a2, all the way up to an minus 1. And again, if I give you something in a form that is this general, the odds that you'll be able to say anything useful about it is almost 0. So we try to restrict to recurrence relations that are both solvable or approximately solvable and have some applications of modeling things in the real world. So there's lots of recurrences you've seen. So here's a nice example. an is, an plus 1 is n times an. There's actually dispute, it hasn't quite come to fighting yet in the community as to do you write an plus 1 equals or do you write an equals. There's advantages and disadvantages to both. The advantage of writing an equals an minus 1 is the coefficient here is the same as the minus 1 over there. It just throws off your normalization by about 1 unit. Doesn't make a huge difference. So I could write an plus 1 is nan, or I could write an is an minus 1. Are these the same? Is this recurrence the same as this recurrence? All right, let's find out. So when I give you a recurrence, I have some way of getting later terms from earlier terms. I also need one other piece of information. What else do I need? Yes?
A base case.
A base case or potentially base cases, depending on how long it is. Since I get each term from the previous, I only need to know the initial values. So let's say a0 equals 1. Let's say a0 equals 1. So now if we look at the first one, so first one, we have 0. And then when I plug in n equals 0, I get a1 is 0 times a0. I'm sorry. I get 1. Sorry. Now when I plug in n equals 0, I get a1 equals 0 times a0, which is 0. Now I plug in n equals 1, and I get a2 is 1 times a1, which is all right, in the second case, I now get a1 is 1 times a0, which is 1 times is 1. a2 is 2 times a1, so 2 times 1 is 2. a3 is 3 times a2, which is 6. And if I do one more, a4 would be 4 times a3, which is 24. And in fact, somebody has said, oh, that's just 4 factorial. And in fact, this recurrence relation is so famous, it has a name attached to it, the factorial recurrence. So these two recurrences, they look a lot alike. Is there a way to change the initial value here, maybe, so that this becomes the same as this? Notice that there is a little bit of a difference. Here I have an index of n minus 1, and I'm multiplying by n. So there are some small differences. So as a nice exercise, can you maybe change the value of a0 so that this might actually work out? So I'll leave that as an exercise. So in the first case, in the second case over here, we have the factorial function. Is there a formula for for the factorial of the nth number? Do you have a closed form expression for it? So if I want 2014 factorial, what is 2014 factorial?
2014 times 2013 factorial.
Well, that's just the recurrence relation. I want a simple formula for 2014 factorial. Do we know a simple formula for it? I was really hoping somebody knew. That's just giving it a new name. Just like, if I say that, something is square root of 2, do I have a good formula for that? So again, just because I've given something a name does not mean I have a good way of writing down and getting a hand on what it is. And you've got to be very careful about that. For the factorial function, just because I call it now 2014 factorial does not mean I truly understand what it is. I have ways of approximating it, but in terms of what is it actually, that's much harder. Let's look at another recurrence. an plus 1 is 2an, and let's say a0 equals 1. Okay, so the first term is 1. What's the next term? 2. In fact, it just says multiply by 2 every single time. 2, 4, 8, 16, 2 to the n. Do we have a nice formula for the nth term of this? So I think we all agree we'll accept 2 to the n as a nice form. Will 2014 factorial not as nice? But again, we've introduced the exponentiation here. We've introduced the factorialization here. Right? This is not that hard to solve. So the question is, when are you able to solve relations? So fn plus 1 is fn plus fn minus 1. This is the Fibonacci recurrence, one of the most important of all the recurrences. And we need initial conditions. What should the initial conditions be? f0 equals, f1 equals, what should we choose?
1.
I'm sorry?
0 and 1.
Yeah, I'm going to ignore the people who don't say the ones I want. 0 and 1. In some of the research I do, it's actually more convenient not to have the Fibonacci numbers go 0, 1, 1, 2, 3, 5, but to have them go 1, 2, 3, 5, 8. And maybe later today I'll just talk about why you might want that. It's essentially the same sequence. So we can calculate 1, 2, 3, 5, 8, dot, 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 dot. Very early in the Project Euler problems, you will encounter the Fibonacci numbers. They were, I think, initially started by trying to model populations of rabbits. And you're trying to calculate, given how many rabbits you have now, how many rabbits do you expect to have in the future? Is it hard to calculate Fibonacci numbers? If I want to extend this beyond 8, can you do it? Okay, so what if you wanted the 100th Fibonacci number? Can somebody give me an algorithm, a procedure that will give me the 100th? How can I get the 100th Fibonacci number?
Having the 99th Fibonacci number.
Okay, and how do I get the 99th and 98th?
We have to keep going backwards.
Good, keep going backwards. So if I start all the way in the beginning and work my way up, I can calculate the 100th Fibonacci number. What if I wanted the 1000th? Can I do it? Oh, by the way, I have a computer with infinite storage, infinite precision, infinite computational power. Is that going to be a problem? No. In the real world, when I don't have that computer, however, it's going to be painful to calculate the 1000th Fibonacci number. We have a procedure that will work. And I apologize, I've just been teaching linear programming for an hour, all about efficiency, and so I guess that's still on the mindset. I want a way to jump to an arbitrary Fibonacci number. And so I want ways to solve recurrence relations. So what I want to do is I want to show you how to solve certain types of recurrence relations. These occur on an enormous number of contest problems, and then we're going to apply them to some various things. So fn is 1 over the square root of 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. This is Binet's formula. I believe we've mentioned this formula in class. Okay? Did we talk about this before? I'm sorry? No. Okay. What can you tell me? What kind of numbers are the Fibonacci numbers?
Is that written right?
I think so.
I might be missing something obvious, but wouldn't it just get to 0 every single?
No, I have 1 plus root 5 and I have 1 minus root 5.
Okay.
No problem. What kind of numbers are the Fibonacci numbers? Integers. So if there was a police lineup of numbers, one of the numbers was causing you troubles on your homework, and you had to identify to the police which number it was, and would you pick this out of a police lineup as an integer? Why not? It's got square roots. Anything else? It's got divisions. All right, this does not look like an integer. You check a couple of values, check n equals 0, 1, 2, 3, 4, you'll see it agrees with the Fibonacci numbers. This leads to one of my favorite methods of proof. It's the method of divine inspiration. So the way you solve a problem is you write down the answer and you show the answer works. This is a valid form of proof. What is the problem with this method of proof? I'm sorry? Oh, well, you don't have to have the answer. You just have to be divinely inspired, and the answer has to come to you. Right? So if you don't have the answer, it's okay, but you need to somehow get that answer to you. Are you always going to be divinely inspired? Damn it, I was hoping somebody would say yes. But if I know this answer, though, I can plug this in and see if it works. How do I do this? I show that when I put in n equals 0, I get this. I show when I put in n equals 1, I get this. And I show it satisfies the recurrence relation. If I can do all that, the recurrence relation uniquely determines the sequence once I've given you the initial conditions. Okay? You can also do proofs by induction. You can assume the formula works all the way up to n, and then show it works for n plus 1. So a lot of books talk about recurrence as a very natural thing to follow induction. Since we've spent a lot of time on induction, I thought this would be a really good time to discuss recurrences. Does this look strange? Okay. What I want to do is I want to show you two different ways to get the solution. I'm going to concentrate on constant coefficient recurrence relations. Linear algebra is a prerequisite for this class. Yes? Okay, good. So we'll be able to use a little bit of linear algebra. So let's assume we have a fixed length, constant coefficient recurrence. So maybe we have an is c1 an minus 1 plus dot 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 plus c k an minus k. So the idea is guess an equals r to the n. So I'm going to guess my solution has this form. Why is this a good thing to guess? Well, if you look at the special case when an plus 1 was 2an, we actually saw we had a solution of that form. The solution was of the form 2 to the n. So maybe it's not so unreasonable to guess that we have some kind of exponential growth. And if we plug that in, we get r to the n is c1 r to the n minus 1 plus ck r to the n minus k. I bring everything to the other side, and then I can pull out an r to the n minus k. And I get r to the n minus k times r to the k minus c1 r to the k minus 1 minus dot 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 minus ck equals 0. This is called the characteristic polynomial. So if this whole expression equals 0, there's two possibilities. Either r equals 0 or r satisfies this equation. Well, let's think about what would happen if r equals 0. Then I'm guessing an equals 0 to the n. Will 0 to the n satisfy this recurrence? If I let an equals 0 to the n, will that always work? Yeah. Is it interesting? No. And it probably won't satisfy the initial conditions. So I really don't care so much about this part over here. This is the part I care about. Every time I get a root of this equation, I get a new solution to the recurrence. And then I'm not going to go through all the algebra. I will leave this as an exercise for you to do. But it turns out if you have two solutions, you can actually combine the solutions and make a new one. So what we're going to do now is, if r1 to the n dot 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 rk to the n are solutions, so is alpha 1 r1 to the n plus alpha k rk to the n. So linear combinations of solutions are solutions. The reason this is true is because we have a linear recurrence. So the way you would prove this is you would just plug this in, and you would basically just show I can group things together. I group all the r1s together, and I get the characteristic polynomial multiplied by alpha 1. I group all the r2s together, I get the characteristic polynomial evaluated at r2 times alpha 2. I group all the r3s together, I get the characteristic polynomial at r3 times alpha 3, and so on.
So I would believe that this gives you a solution to the recurrence relation, but in terms of linear algebra, we saw characteristic polynomials.
Right.
The determinant of a minus lambda I.
Mm-hmm.
So it's a polynomial in lambda. Why should we be thinking of this in sort of the same vein?
Why should we or should we not?
Why should we? Or this is just a coincidentally?
No, there are ways to write this in terms of linear algebra. And you can write the Fibonacci numbers as a vector. And if there's time today, I will talk about trying to write it like that and just trying to get a unified theory. Now, one of the things I'm assuming here is I have k distinct roots. And now all I need to do is I need to find what are the choices of the alphas. And this is where you use linear algebra. So you get a system of equations. So you would get alpha 1 r1 to the 0 plus alpha k rk to the 0 equals the 0th term in the series. And then I need to do this, I think, k minus 1 times, k times, and then that will give me a huge matrix. Alpha 1 r1 to the k minus 1 plus alpha k rk to the k minus 1. And you can actually write this in matrix form for the alphas. Alpha 1, alpha k, a0, ak minus 1, and then you'll get all 1s in the first row, r1, r2, rk in the second row, all the way down to r1 to the k minus 1, rk to the k minus 1. What do you hope is true about that matrix? Invertible. If the roots are all distinct, it turns out that this matrix is invertible. This is called a van der Maan matrix. And if roots are distinct, it's invertible. And if it's invertible, then we can solve for the problem. Okay. Do you want to see a specific example and go through the calculation for the Fibonacci numbers? Okay, so at least a few people are shaking their heads yes. So let's do it for the Fibonacci numbers. And I'll talk briefly about what can go wrong. So we have fn plus 1 is fn plus fn minus 1. So we have r to the n plus 1 is r to the n plus r to the n minus 1. So we bring things over. We get r to the n minus 1, r squared minus r minus 1 equals 0. If you do not know how to solve a quadratic polynomial, fortunately we covered that in linear programming today, and you can just watch the video there. We get r equals 1 plus or minus the square root of b squared minus 4ac, which becomes 5, divided by 2a. And so we get fn is alpha 1, 1 plus root 5 over 2 to the n, plus alpha 2, 1 minus root 5 over 2 to the n. And now we just have to figure out what alpha 1 and alpha 2 are. We can use any Fibonacci numbers we want. Why not make life easy and use the smallest ones? So what we're going to do now is we'll take n equals 0 and n equals 1, and we'll get two equations in two unknowns. So we get alpha 1 times 1 plus alpha 2 times 1 equals 0. And then we get alpha 1, 1 plus root 5 over 2 plus alpha 2, 1 minus root 5 over 2 equals 0. I could put this in matrix form. I could use linear algebra. It feels like overkill here. What can you detect from the first line? So what do we know from the first line? Alpha 1 equals negative alpha 2. So we have 1, 2. So 1 tells us that alpha 2 is negative alpha 1. So 2 becomes alpha 1. And now I have a minus sign. So I have 1 plus root 5 over 2 minus, I'm sorry, this is not a 0, this is a 1, sorry. Minus 1 minus root 5 over 2. The 1's cancel. The root 5's reinforced, and I get 2 root 5 over 2, which is just square root of 5, equals 1. Therefore, alpha 1 equals 1 over root 5, and we have alpha 2 is negative 1 over root 5, and we get Benet's formula. Fn is 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. Okay? And there's Benet's formula. This is absolutely wonderful. We've got a little bit of time right now. Let's think and glean from this. What can you tell me? How big is 1 minus root 5 over 2? What can you tell me about its size? Big, small, positive, negative, complex?
Small negative.
Small negative. It's less than 1 in absolute value. Square root of 5 is between 2 and 3. That's the level of detail I need, okay? Square root of 5 is between 2 and 3, so 1 minus the square root of 5 is between negative 1 and negative 2. When I divide by 2, it's between negative a half and negative 1. This is less than 1 in absolute value. What happens if you take a number less than 1 in absolute value and you raise it to a high power? It's damn small, right? So this is essentially gone. The nth Fibonacci number is approximately 1 over root 5, 1 plus root 5 over 2 to the n. Basically, just take whichever integer is closest to that if n is large, and that's your Fibonacci number. Okay? So this is how you would solve recurrences like this. Any questions on Fibonacci? Yes?
So this is why, as n goes to infinity, the ratio between the Fibonacci numbers approaches the goal.
Yes. Excellent observation. So if you want to look at fn plus 1 divided by fn, when n is really large, fn is just this, fn plus 1 is just this with n replaced with n plus 1. This part doesn't really matter. And that will give you that the ratio of the Fibonacci's converge to the golden mean. I want to make one comment about general recurrences, and then we will start doing some problems. So things were very nice here because we had distinct roots. If we don't have distinct roots, it's much harder. And then the question becomes, you don't have enough solutions. How many of you have taken a class on differential equations? Wow, that's more than usual. That's good. So the question is, what do you do if you have repeated roots? So if R is a root of multiplicity m of the characteristic polynomial, use r to the n, and r to the n, and squared r to the n, and how high, what power of n do you think I go up to?
M.
Why m? How many roots would that give me? How many solutions would that give me if I went up to the mth?
Oh, M minus 1.
I have to go up to m minus 1. Because I start off here, I can write this as n to the 0. And it turns out these are the extra solutions you need. And you can write anything now. Instead of just the roots, you have to be a little bit more careful and take these combinations in as well. Okay. So we have two possibilities. We can go on and we can do some problems, or I can show you how to solve this using generating functions. I'm sorry? Some problems. Okay. So the homework problems hopefully look a lot more like recurrence relations now. So we had a 3 by n board, and we had 1 by 2 dominoes. And we wanted to try to cover. So how did people try to tackle this problem? What did people try to do? Any thoughts? Yes?
Well, we started it by just drawing it.
Excellent. So we quickly learned n has to be even. All right, so if we have n has to be even, the first case is n equals 2. How many solutions are there? 3. So we can go in this configuration, we can go in this configuration, or we can go in this configuration. There's 3. All right, what do we do next? Add 2 more. Whoops, I shouldn't have done it that way. Oh well. All right. How do you go through the cases here? Yes?
I did 2 of the 2 by 3s for the 3 by 2s.
Okay.
And I looked at the solutions that would cross the middle line of the dot.
Okay, so you went for crossing the middle line. Okay. How else did people try to do it?
I thought about 2 cases. One, I looked at the bottom left corner.
Okay.
One where you have a vertical in the bottom left corner, and one where you have a horizontal.
Okay. So this is breaking up into cases. Case 1, it goes like this. Case 2, it goes like this. And if you go like this, you know the next one has to be going like this up top. And now you have 2 possibilities here. You either go down, in which case you've reduced to a previous problem, or you have to have 2 things like this. And if you have 2 things like this, what comes next? Has to be like this. So the idea is somehow can you get a recurrence relation from this and express how many there are in a 3 by n plus 2 board in terms of smaller boards. So was anybody able to get a recurrence for this? And so here, if you do something like this, you very quickly come down to counting how many solutions there are in a configuration where your board is a little bit changed. And so you may want to introduce auxiliary variables in your recurrence. And I might want to try to solve that recurrence. What if we had the one that was like this now?
Same thing could happen.
So if it's like this, we could have several possibilities. We could have 3 things like that. We could have 2 things like that. Or, yeah, it could be like this, and then 2 things like that overhanging. And notice that this brings us back to a configuration that we've seen before. So what you want to do is you want to have 2 different variables. How many solutions there are in the whole board, and how many solutions do you have when you've, say, removed 1 corner? Or maybe added 1 extra corner, And then you're going to have a recurrence in 2 variables. Okay? So I'm going to have the first homework assignment be just pure extra credit. Any points you get here is absolute gravy. Okay? What problems do you think are going to occur in the second homework assignment? I'm sorry?
The next topic we're learning.
This problem. Right? Now that we've done recurrences, right? Revisit this now and see, if you didn't see a way to write down a recurrence for this before, try to write down the recurrence and see if you can solve it.
We can get our old homework back before the next one too.
Yes.
Cool.
You can get your homework back.
Are you going to put the correct answer?
No, the TA will not put the correct answer. Yes. if you're able to. So if you're able to find an explicit solution, that's great. Another thing that's worth mentioning, have I mentioned these letters to you before? Okay. The online encyclopedia of integer sequences. If you have the first few terms in the sequence, you can plug this in, and the online encyclopedia might even tell you what the recurrence relation is, what the solutions are. It's a wonderful, wonderful resource to have. I'm sorry? Online encyclopedia of integer sequences. I can spell some of those words, but my spelling is not good enough to get an encyclopedia. Integers, I think I can do. All right. So let's do another recurrence relation. This one might be a little bit harder than what we've been doing, but it's one of the most important ones. So this is a very standard problem. So you have an n by n board, and you cannot go above the main diagonal. And you can only walk north or east. It's okay to be on the main diagonal, but you can't go above it. Okay? So the question is, how many paths are there that start in the bottom and end in the top where I never go above the main diagonal? How many of you have seen this problem before? Some of you should have seen this. Okay. If you've seen this before, don't speak up. What should we do when we have a new problem like this that we've never seen before? Do some cases. So first case, the 1 by 1 board. You're never allowed to go above the main diagonal. You can only walk north and east. How many? There's only one way. I hear something being moving, which is amazing because I didn't think there was anybody else down here. All right, now what do we look at? 2 by 2 case. How many paths are there?
2.
So we can go over, over, and then we have to go up. That's path 1. We can go over, up, then we have to go over, up. So there's only 2 paths. So in the 3 by 3 case, the answer will either be 3, 4, because it could be just all the positive integers, or maybe powers of 2, or maybe it's Fibonacci numbers, which would also give me a 3. Anybody buying any of this? No. All right. We do not have nearly enough data to conjecture at this point. What the pattern is that starts 1, 2. We need more information. All right. How many paths do we have now? 4. So let's go in order. We can go all the way over and up. That's 1. Okay. So let's see. I do believe 5 is correct. So 1 is going all the way over and up. So instead of taking 3 steps over, what could we do? 2 steps. So if we do 2 steps over, we do 1 step up now, so we're here. And now we either go over and then it's determined, or we go up and it's determined. So there'll be 2 more paths from that. We could take just 1 step over initially, and now what do we have to do? All right, now how many paths are there?
2.
Why is it 2?
It's the same as I thought.
Ah, that's useful. Right? Once we've hit this point, we're now back to where we were before. And so from that point, it's just 2 more. And now we can begin to see a recurrence.
I'm still confused about what the rule of you're not allowed to go above the main diagonal.
Right, so for instance, I can't go here, up to here, back to here, and up to here.
We're not looking at the blocks.
Right,
We're looking at the actual line.
We're looking at the actual lines, the path on the grid. So, this is one of the few things I like about New York City. We're in Manhattan. We have a beautiful grid to walk through. Okay? So anybody have any idea about how we could develop a recurrence for this? So I want to somehow break things up into what we've done before. Yes?
Well, like, there's always going to be a smaller n by n square embedded in the bigger one.
Okay.
And one path will always take you to the extreme diagonals of the smaller square. At least one.
What if I take the path where I go all the way over and all the way up?
Right, that doesn't.
I'm sorry?
That's a new path that you can't get.
That's a new path I can't get. Okay. And then otherwise, you're very close. I think it's useful to break things up into an action. So what was nice is as soon as we hit this point, we knew how to handle the rest of the problem. Because that's a case we've already studied. One of the big things is to make sure you never double count. So what we can do is we can always say, let's count all the times we get to the upper right corner going legally, and this is the first time we hit the main diagonal. And then we'll count how many ways are there so that that's the first time we hit the main diagonal. Okay? One of the things that's really difficult is, what if I go here and then here and then here? I've hit the main diagonal twice. I want to be very careful not to double count. And so one question is, how many ways are there so that the first time I hit the main diagonal is there? So more generally, I've got a very large square. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I have something like this. And this is probably horribly drawn, so I shouldn't even try to draw the main diagonal. So, wow, that's bad. All right. So we'll look at like some stretch over there. And I want to say, this is the very first time I hit the main diagonal. And I want to count and see how many ways are there to do it. That almost looks like I'm solving the original problem going from here to here, right? Because that's just a smaller square. What's the problem? Why is it not the same? I could have hit somewhere earlier first. So I've got to make sure I reduce it to a smaller problem that I can know, but that I haven't hit it already. Well, what does my first step have to be? First step has to be east. We know that much. So I know I have to start off like this. What does my last step have to be? Up. So now look. I now have a smaller square in here. And I can move however I want from here to here as long as I stay below this diagonal. And I'll never hit the main diagonal over there. How many ways are there to go from here to here? If this was at k, this would be k minus 1. I made it one thing smaller. So what we get is the number of ways so that this is the first point, this is the first time you hit. So if bk is number of paths from 0, 0 to kk with first main diagonal hit at k, then we get bk is ck minus 1. That's very nice. And now, how many ways are there to get from here to here? So I need to choose legal paths in there. That's going to be c n minus k. We've got to make sure we've never hit any path twice. Are all the paths distinct? So remember, we talked about before, maybe I have something where I come here, then I come here, and then I come here. I could look at this as I've come here, and then I choose a valid path in this 2x2 block, or I come here, and I choose a valid path in this 1x1 block. I need to make sure I don't count the same thing twice. I've done something here that will guarantee I don't count the same thing twice. What have I done? What's the special word I'm using about this point? First. It's the first point where we hit the main diagonal. Well, then that means that there can't, if I'm trying to say, have I counted something twice, no matter what path you give me, it's got to have a first point where it hits the main diagonal. Does every path have to hit the main diagonal at least once? Yes. Where do you have to hit? At the end. Worst case scenario, you hit there. And if you're hitting there, then you have k equals n, you have c0. Okay, c0 is just 1. Great. Otherwise, two different paths. Either they have the same place where they first hit, or they have different places. If they have different places where they first hit, are they different paths? Yes. If they have same places where they first hit, well, then they're a different path in here, and by induction, we've already got a different place. So we now get the following beautiful recurrence. We get Cn is the sum, k goes from, I think, 1 to n of ck Cn minus k. I might have my index off by 1. I think this is what I want to do. So the question is, do I start at k equals 0, or do I start at k equals 1? I can check this out and check the formula in a couple of cases. So I will leave this as an exercise. Is it 1 or 0? So this is a beautiful recurrence. Do we know how to solve this? No. This is not a linear recurrence relation. So I will give you some stuff to read over the weekend about how to solve something like this. It uses a beautiful theory of mathematics called generating functions. So again, I cannot feign the fact that I love the Putnam and I love exams like this. I know this is being recorded. I'm not a huge fan of math competitions. But I love good math problems that are springboards to good things. This leads to the subject of generating functions. How many of you have seen generating functions? How many of you are comfortable with generating functions? Okay, so most of you have not seen them. If you have seen them, if you want, email me and I'll give you some advanced stuff you can read about them in terms of applications to probability. Generating functions is one of the most important tools we have in mathematics. It will provide us another way of proving Benet's formula. And it will also give us a formula for these guys. And this is much harder. And so the reason I like something like this is it's going to be a great way of introducing a useful math technique. So for the weekend, I'll also give you, a couple of things on recurrence relations to look at and just choose some of the problems you want us to look at. Can we now apply this to the dot problem we were looking at last time? So last time, and I'll make this extra credit. So we had n blue, and I'll represent blue like this, and n red, I'll represent red like this. We put them on a circle. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And we wanted to walk in such a way that we never walked through more blue dots than red dots. And we proved that there was always a way to do it. You could look for, never pass more blue than red. And so what we said is, well, we know there's always got to be a situation where we have a red dot followed by a blue dot. And then by induction, we know how to do it at a smaller one. And you can keep playing. So now that we have this, well, we know we could throw away this and go by induction. And then we could throw away this. We could throw away this. This we could then throw away as well, because these are now together. And then these two are now together. So if we start here, we should be fine. Oh, wait a minute. Oh, I circled things the wrong way. Oh, I mixed up my reds and my blues. That's the problem of using white chalk. All right. So, all right. So now here's my question. How many configurations have k legal starting points? So we saw that there were some configurations where there was only one place you could start. What are the possible values of k? As I increase n, how many of them do you have that have exactly k configurations? Can you come up with a formula for that? And so I think these would be great problems to try your hand at. And just again, whenever you get a problem, you want to get into the habit of asking related questions. This is how you write research papers. Whenever I go to a conference or a school, I try to leave with a new research topic. And so in the faculty seminar, I'm going to be speaking sometime, I think, in November now. And I'm going to talk about a project I did with some small students that involved my asking a question when I went to the University of Illinois Urbana-Champaign. Just trying to find a new project. Okay, I think we have about 1 minute left, 2 minutes left. And so what I want to do with the last minute and a half is try to convince you why the Fibonacci number should be listed as 1, 2, 3, 5. How many of you have heard of Zeckendorf's theorem? So I know people who've talked to me have heard of Zeckendorf's theorem. So here is a wonderful property the Fibonacci's have. Zeckendorf's. 1, 2, 3, 5, dot, dot, dot. Every integer is a sum of non-adjacent Fibonacci's in a unique way. So somebody give me a number that's not too large, not too small. 12. So I can write 12 as 8. And now 12 minus 8 is 4. Largest Fibonacci number less than 4 is 3. I'm using a greedy algorithm. 12 minus 8 minus 3 is 1. So let's say I take 32. 8, 13. It's actually, this is a constructive proof. You take the largest Fibonacci number smaller than your number, 21. If I could take the next number after 21, if I could take 13, I could have taken their sum. And then that means this is not the largest number I could have taken. So now 32 minus 21 is 11. So now I add 8. Now I need 3. Right? There's a lot of fun things you can do with Zeckendorf decompositions. One of my favorites, and this goes to Carl Pomerantz, I believe, is you can use this to approximate the conversion between miles and kilometers. How many kilometers are in a mile? About 1.6. Approximately, what's the golden mean? About 1.6. If you write a number in its Zeckendorf decomposition and then increase all the indices by 1, you've essentially multiplied all of your Fibonacci summons by about 1.6. So you've essentially converted from miles to kilometers. This is, of course, much better than just multiplying by 1.6. Right. It's one of the strangest applications of the Fibonacci numbers you have. It's not a bad way to approximate converting from kilometers to miles or miles to kilometers. Okay? So anyways, I will send you some fun stuff to read. Have a great weekend. If you have any questions, just shoot me an email.